Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Who's here for a couple days visiting from hot, sticky Ithaca. And he's going to give two talks. We're working him really hard while he's here. He's going to give a talk tomorrow that's much more sort of machine learning theory. And what he's going to talk about today is an interesting mix of behavioral analysis of people as they search the web and machine learning techniques to learn ranking functions that optimize people's satisfaction with results that come back. So without further ado, I'll turn it over to Thorsten. We have one open slot this afternoon if people are interested in meeting with him, see me after, and that's it.
All right. Yeah, thank you very much for the invitation, and especially to Sue for organizing all of this. So yeah, this is going to be, so I'm a machine learning person, and typically I talk about machine learning algorithms, but this talk's going to be more about, or less about algorithms, it's going to be more about how we're going to get the data to train our algorithms. So I want to talk about how to get feedback or get training data by observing users in web search to improve the ranking functions. And this is joint work with a whole bunch of people, and as Sue pointed out, Philip Rodlinsky, sitting in the front row, the tall guy with the Australian accent here, is actually doing a lot of work, current work on this. And I won't really have time to cover this work. He's just written 2 papers on it, which I'm not going to cover in this talk for time reasons. But if you want to find out more, talk to him. So yeah, so this is joint work with Philip and the people in the HCI group at Cornell, Jerry Gay, Laura Granka, she's now at Stanford, Helene Hembrook, and Bing Pang. They are the people who are actually running all these eye tracking studies and user studies that I'm going to talk about. Okay. So today's search engines are kind of a one-size-fits-all approach, right? Independent of who asked the query, or somewhat independent of who asked the query, we get back the same results. So for example, if you type in my favorite machine learning method, SVM, into Google, the first hit that comes back is a French magazine. The second one is a hit on, of course, a great hit on my page about SVMs. But if that search engine knew a little bit about me and how well I speak French, it probably wouldn't have put this first. Now, I think one area where we can make retrieval better is by taking into account who the actual user is and what the preferences of the user are. So, I mean, all in all, this would have probably been a pretty good ranking for me because it does actually talk about this, the machine learning method SVM. This is what happens if you type SVM into MSN search. What it retrieves here are actually quite a lot of German links, and in particular, like things about German soccer. There's the Sportverein Meppen, which for me wouldn't be a good ranking, but actually for my dad, who's a big German soccer fan, he probably would have preferred this ranking. So I think when we want to talk about web search, one way to make web search better is by taking into account who the user is. Also, I think by taking into account what the collection is. So for example, with Philip, we're doing work on internet search for different applications, ranging from like library search to web search. And clearly, the same retrieval function applied to both problems is not going to work equally well. So I think we want to tune retrieval functions not only to particular users, but also to particular collections. Now, clearly, doing this in practice is going to be hard if you can't automate it. So I believe, I don't know really what you guys are exactly doing, but I believe that there's a lot of hand tuning involved or manual work involved if you want to tune a retrieval function. So maintaining a retrieval function for like every person on the planet or for particular user groups is just not feasible. I think one way of overcoming this problem is to use machine learning techniques and use feedback from the user to learn improved retrieval functions automatically. So and this is what I want to talk about in this talk. I want to talk about methods for improved retrieval functions, and how to get feedback from the user about the relevance of documents. So these are the two questions. So first question that I'm going to spend probably 3/4 of the talk on is, how do we get training data for training our machine learning algorithms? How do we get data telling us this about the relevance of a page to a query? And then the second question attaching to this, once we've identified how we can get this data, how can we use this data, and what are machine learning algorithms to actually learn improved retrieval functions? So let's start with the first question. Now, we need feedback from the user. So one naive way of getting feedback is to ask the user. So ask for explicit feedback. So if, for example, we could have a little, I don't know, checkbox next to every hit here, and the user could like click it to say this is a relevant link or not. But my experience was asking users for this kind of explicit feedback, especially in such a low involvement context like web search, is that they're not going to participate. There's maybe a small fraction that's going to participate, but I don't think this is going to get us very far. Now, what I believe we can use instead is something which you could call implicit feedback. So if I observed your searching behavior over a week, let's say, and I just knew what were the queries that you typed in, what are the clicks, how much time you spent looking at particular pages, how you moused, how you scrolled, I think I could figure a lot about what your preferences are and what your interests are. The nice thing about this is really easily observable through a search engine, like queries and clicks. So we can get pretty much unlimited data. And we can get data for pretty much any person on the planet. Not just if you look at, for example, hypertext structure, which is just a very small subset of users which create hypertext structure. For example, my mom would never create a web page, but she uses a search engine every day. So you would get data from her as well. But clearly, this data from implicit feedback is going to be harder to interpret. We have to translate the observed behavior into some meaningful feedback that we can use to train our algorithms. And that's going to be more difficult, clearly. So now, what I want to talk about is how can we take the observed behavior and turn it into something that we can train our algorithms with. And let's focus only on queries and clicks, actually, just because this is kind of the first thing that came to our mind. But I think there are many other indicators that we could use. So let's go through an example. Let's say we have this ranking presented to the user for the query support vector machine. And we see that the user clicks on link 1, 3, and 7. Now, what could we possibly deduce from that? Well, we could interpret this as a kind of an absolute feedback. We could say, well, clicked links are relevant, not clicked links are not relevant. So this would be an interpretation of clicks as giving us some absolute relevance judgment. And so we could assume user goes from top to bottom here, and not clicking on this link means this link is not relevant. So this would be an interpretation of clicks as absolute feedback. Another interpretation that we could come up with is what I call relative feedback. So again, let's assume the user goes from top to bottom, reads the links, and whenever the user skips a link and clicks on a link lower down, what this really means is not the clicked link is relevant on an absolute scale, but it really only means that this link is more relevant than the link that was skipped earlier. So what we get from relative feedback is these pairwise preferences. So this link is more relevant than this link, and this link is more relevant than this one, this one, this one, and this one. So relative preferences. Well, this one seems to be stronger. This one seems to be a bit more plausible, maybe. So what we've done is we've created a user study to investigate which of these two interpretations are actually correct, which are accurate. Are they both accurate, or are they both not accurate, or which one of the two is? So can we actually get reliable feedback from these implicit observations? And we addressed this question in 2 steps. So first we wanted to get some insight into what's the decision process of the user when the user sees a results page and decides where to click. So first we did a user study that just looked at addressing these questions. So for example, what I've implicitly made as an assumption before is that the users read the list of results from top to bottom. Is this actually correct? That seemed to be a vital assumption in both of the previous strategies. How many abstracts do users actually evaluate before they click on something? Clearly, if the user hasn't evaluated an abstract, trying to induce any feedback for that abstract just doesn't make sense, right? Do users actually view all the abstracts above a click, or to what extent that this is true? So if they go down to link number 4, have they actually looked at 3, 2, and 1? And do users look below a link before they click on something? Once we have a reasonable idea of what this decision process is, we then started to look at what are these 2 interpretations and how far are these 2 interpretations correct? Can clicks be interpreted as absolute feedback, or can they interpret it as a relative feedback? So we've conducted a user study that involved both eye tracking to answer the first set of questions and relevance assessment to answer the second set of questions. So the study is set in a web search setting, and we used Google as our search engine. And we essentially asked users to come into the lab, get hooked up to the eye tracker, and then answer 10 questions for us. And these 10 questions were the same for all users. So during the search, we recorded their eye movements to have an idea which abstracts they read. And afterwards, we got relevance assessments for all the pages that they visited. And then we can compare these relevance assessments to the judgments that we extract from implicit feedback. By the way, if you have any questions, just feel free to ask.
I just have a question about eye tracking. I mean, do we know how much, I don't know, do you wear a thing when you eye track, or just looking at your eyes? Or, I mean, the real question is, do you know how much that affects people's action? I mean, would you trust that somebody being eye tracked acts the same way that they would if they were in their room doing it?
So let me skip ahead a little bit. So the eye tracking device that we've used is a camera here that records a reflection in your eye, and from that reflection computes back where you're looking on the screen. So you don't have to wear like a bulky thing. The only thing that you have to wear is this sensor that tells the system where your head is in relation to the screen. We also set the study up that we didn't tell the users exactly what we were interested in. So we told them just, we're interested in how people find information on the web. But we didn't restrict them in any way. And we didn't actually tell them that we were particularly interested in how they behave on the Google's results page.
But you know, for instance, one thing you could do is look at how many clicks. And I think if I'm tracked like that, I don't want to look stupid. So I'm very careful about clicking. You see, like on average, how many clicks are there with that mechanism versus without? And if they're the same, that's good news. If they're way different, then that's good.
Right. So, I mean, I think that's probably something about general lab settings that this might be misleading. And no, we haven't done the check how this behavior in a lab setting relates to behavior in a normal setting. But we try to be as unrestrictive as possible. So let me give you a little more details about the experiment setup that we used. So we asked 36 undergraduate students who all claimed to be familiar with Google. And we gave them these 10 questions here. And some of these questions are kind of more informational, like finding a fact, like who discovered the first modern antibiotic. And 5 of the questions were finding a homepage, like the homepage of the Carnegie Mellon graduate housing. These questions were read to the user, and the user was then just asked, start with Google, and then find me the information. They could reformulate queries. They could go off. Actually, there was one query about a movie. Yeah, here, about the Time Machine movie, who was the actor in that movie. People could just use Google to find the IMDb and go there and search there. So we didn't restrict them in any way. And as I said before, we didn't exactly tell them what we were interested in. We just told them search, and they didn't know that it was the Google's results page that we were really interested in. So this eye tracker essentially gives you the scan path of how people look through the page. People look at, people read during fixations, which are longer amounts of times where the eye stays fixated on a particular piece of the page. And then it's moved in saccades to a different position. So what you get is this sequence of points where the person looked. There's some accuracy issues with the eye tracker. So there's first of all, there's a certain viewing angle that you can perceive when you fixate on a point. And there's also a measurement error in the eye tracker. But for these types of accuracies that we're looking at, it was pretty good. So essentially what we just wanted to know is whether fixations fall into these 10 look zones on the results page. So essentially around every link that we presented, we created a look zone, and then we asked, did the user fixate in this look zone and how often? So this was our level of granularity at which we kind of aggregated the viewing, the eye tracking results. So we also piped all the communication between the user and the outside world through an HTTP proxy that actually removed ads from the Google page just to make the pages more uniform. And it also recorded all the pages that were viewed and all the pages that were ever presented in the results page so that we could have a cache and go back later and see exactly what the pages were. These manipulations were not detectable by the user. So this looked exactly like a normal Google page. It also didn't have any significant delay. So let's look at how people view this results page. So first question, how many abstracts do they look at before they start to first click on their first link? And it turns out that it's a fairly small number. So the mean number of links that they look at is 3. The median number of links that they look at is 2. So on average, they evaluate 3 links or 3 abstracts before they make their first click. So we can't assume that once the user clicks on a link on the page, that it's actually like an informed decision over all 10 hits that were presented. Yeah. I believe if you had a different presentation of the results, for example, smaller abstracts, that might change. Different color scheme, I don't know. No, we didn't give them an explicit time. We did stop them after a few minutes, I think like 3 or 4 minutes per question, if they obviously weren't getting there. But there was no, for example, there was no reward given for finding all the results, right? Like that.
But there was nothing at all mentioned in that they would try and get it, even if there was no explicit reward. Was there any speaking up front that they would try and do this?
No.
How many items you show per page?
So exactly that's what's going to show up on this graph here. So this is looking at so the question is, how do they actually view the results? So they view them in order. And so this is the rank of the result here, and this is the number of the fixation that in which they first get to this result. So the first fixation, second fixation, third fixation. So, and roughly for the first 2 results, they get there within the second and third fixation. And it's fairly similar, right? The third result so they seem to study the first two results somewhat thoroughly first before they go to the third result. Then it goes up, and then there's another jump here, and that's exactly what you were wondering about. So on our screen, typically, the first 5, 6 results showed without scrolling. And we see this effect quite a lot, that there is a significant effect where people have to start scrolling.
For the first ranked result, why is that number not 1? What are they looking at before they look at the first result? Or is that until they click, so they look at 1, then 2, then 1, and then click or something?
They could have started with number 2, right? Or it was number 3, probably somewhat unlikely, though. So kind of on an aggregate level, on average, people do seem to read the results from top to bottom. So now let's look at that in a little more detail. So this graph shows where people look. So this is the rank of the result. The dark bar here is, the light bar here is the average time spent looking at that result, at that rank. So as you can see, number 1 and number 2 receive the most attention. The most time is spent looking at them. And again, there's a drop to number 3 here. And after number 6 here, it stays kind of flat. So it kind of, again, it means kind of once people start scrolling, this seems to receive, kind of, they all seem to retrieve somewhat equal amounts of attention after that. But really, there's a significant effect that people need to start scrolling, essentially. And so this is like for the 11th link, going to the next page happened extremely rarely in our study, actually. Now, the interesting thing is to compare this against the number of times that the link was clicked on. So this is the dark bar here. So link 1 and link 2 receive almost the same amount of attention, but if you look at how often link 1 is clicked versus how often link 2 is clicked, people overwhelmingly click on link number 1. And there could be 2 reasons for that, right? Either link number 1, Google is just great and presents link number 1, always the most relevant link, or people have some bias and some trust in Google to prefer the first link. And we're going to get back to that question later. Here's a little more detail again, looking at how, if people look actually below the link that they've clicked on, before they click on the link. So let me highlight this. So what the columns mean is people clicked on the first link, the second link, the third link, the fourth link, sixth, and so on, right? And what the rows say is the percentage of queries where this link received at least one fixation in that look zone. So as you can see, if people click on link number 1, the probability that they've previously, before they do that, evaluated link number 2 is roughly a half. But if you go further down, it goes way down, right? And that pretty much goes all the way across, that the next link is maybe looked at with a probability a half, but people typically haven't looked at anything further down when they make the click. Yeah. Common, yes. What was another question? Yeah. That probably means that the eye tracker has some error. So, yeah, but you kind of need to position the mouse, right? And you kind of need to look at it. So I think this gives you somewhat of an idea of how accurate the eye tracker is. Yeah. I think we're not counting that, though. Yeah. And actually, nobody in the whole study did that. Yeah. Mm-hmm. This column 6. Well, actually, we had very few people who clicked on the on the 6th item here. So the error bars on this are huge. It just didn't fit on the table here. But what this would mean is, if they click on the 6th link, the probability that they've previously looked at the first link is 45%. Could be, yes. Here again, you see an effect of the page break here, what's visible without scrolling. So after number 5, typically there's no, or sometimes there's no number 6. So but I think what we can conclude from this is that people typically do not look at the further down links before they make a click. Maybe the next one, but that's it. Mm-hmm.
So it seems like people don't typically look at the ones above them either, because the numbers there are lower than the numbers above each highlighted box are lower.
So
they're more likely to,
right. So the
to number 4 than actually look at 1, 2, 3, 4.
Right. So the one that's right ahead of it, that typically receives a larger. That's more likely to be looked at. The further you go away, the less likely is it that people have looked at it. But there's an asymmetry. So if you go 4 away to the bottom, you're at 4%. If you go 4 away to the top, you're still at kind of 50%. Right? Mm-hmm. Say again.
What's the duration of time that people have to look at the snippet in order to track it?
You have. So what we recorded is have to have one fixation in this look zone. One fixation is like 0.2 seconds. What we're not really accounting for actually is that you have kind of an angle that you can see. And so actually, probably some of these values are going to be larger if you take into account that you have a certain viewing angle. And people use, like, Google uses bold facing, so you can actually spot, well, I'm not really the expert on this, but people tell me that you can spot these things even if the fixation is a couple of degrees off. Yeah. Oh. Yes, we did, and I'm not going to talk. I don't actually have the slides for that. There was a significant difference in many aspects between male and female, actually. I have to refer. So these things are actually in the master thesis of Laura Granca, and so I can point you to that thesis. And she looked at a lot of things, which I can't recall. Yeah.
But the columns are all conditional on you clicking on the
Yes.
item, right? And so you almost never click on the 4th, 5th, and 6th item.
Right. So that's why the error bars here are pretty high. Yeah. Mm-hmm.
So what do you do about the same user clicking different links on the same search?
This is only, so what we're considering here is only the first click that they're doing, just for simplicity. I don't remember the distribution of clicks per page. Yeah, but they're actually not that. I mean, it goes down pretty fast, I think.
It seems like, I mean, that might, if you had that explain the 6th column where you click on the first link and then realize it's all rubbish, so then you scroll down.
Yes. Yes. Probably that would change the, yes.
What I do is zoom in on the fifth one portrait without regard to anything before it, and I'm actually the relative more than
Right. So there is going to be an issue of accuracy, and we're actually going to evaluate that when we compare against the absolute relevance judgment, the manual relevance judgments that we got from different set of judges. what I do think is that these numbers are actually somewhat lower than reality because we did not take into account the viewing angle that people have. But we would have to look into that in a little more detail.
But the bigger problem is that you're viewing, that the measure, where people click first is not necessarily a good measure, right? Because, say, they click something based on the abstract, what you didn't want to know is if they accomplished their task in that. So, some measure as to how often they have to come back to look at the link and
right.
stuff like that. Because where they click first is, as you pointed out on the data, is very much a function of simply, that's the one that got the measure.
Right.
But that's not necessarily the one that helps them get where they want to go.
I agree. So to some extent, that's going to be kind of reflected in the absolute relevance judgments that we're going to get from the judges later. So there we have a judgment of how relevant the page is. It doesn't really tell us whether it accomplished their task on a bigger scale. But we're going to have some grounding of how useful the result is in that. 36. And actually, the eye tracking data show the eye tracker is kind of iffy. Some people seem to have funny eyes and can't be calibrated. I think this ended up data being from 29 people or so, for which we could actually get reasonably accurate eye tracking data. Okay, so let's make some high-level conclusions about how people view the results, which can guide us in designing strategies for how to interpret the results as the actions as relevance feedback or implicit feedback. So most frequently, users view only 2 abstracts, so a fairly low number. They review the results somewhat in order from top to bottom, but they do tend to skip over links. Users view link 1 and link 2 more thoroughly and more often than they view the other links. So there seems to be a particular focus on the first 2 links. But what they end up doing is they are clicking on the first link much, much more frequently than on the second one. And people typically do not look at the links below the one that they clicked before they do the click. So, question?
What is the average number of times that you usually refine before it becomes a task?
You know that, right?
I think in this study, the average number of refinements per task was 2.2. But obviously, because this is a lab study, people are actually probably more likely to refine. But then again, they're going to be... Yeah, just because it's a laboratory setting with someone sitting there saying, here's a question, please answer it, and here's the next question. But one, they're not giving the chance to come back to it later. But on the other hand, they're giving some slightly more pressure to the answer. So I think the refinement question is something that we can't really look at that much.
From the other data we look at it from 25 to 30.
So there's a 25 to 30%.
You have the number of
So if I want to accomplish a task, how many queries can you get? That's not always the first query that you get.
Right.
In this study,
in this study.
in the real world, it's less.
In the real world.
So then that's make it take whether or not they actually succeeded or not. In the real world, even less than 2.5.
Okay. Okay.
The point is here that it's missing the important comparison here between, so Google typically gives you a rank ordered by relevance. So showing that, so here your conclusion is that people are using some kind of threshold model, so coming across links they like the most of people immediately. But in order to support that kind of model, a simple threshold model, you need some important comparisons where you have the rank randomized and you still do the same behavior.
Thank
so
you.
in our experience, you don't see that.
Yes. And that's exactly what the next slide is about. So we actually did a phase 2 of this experiment, which is the same as phase 1. We invited another 16 subjects, again undergraduates. But we randomly assigned each subject to one of these 3 conditions, where we did manipulate the ordering that the results were presented in. So roughly a third received the normal Google ordering, just to replicate essentially the previous study and see if things align. The other group had an ordering where the first 2 links were swapped, and the third group had the whole top 10 reversed. So this was done in this proxy that filtered all the results. And it was done in a way that it was not detected by the users. So we asked all the users afterwards, did you notice that we messed with, well, we didn't ask the question. Did you notice anything about the search engine? And they all didn't suspect that we messed with the results. We also got, again, manual relevance judgments about asking judges to give us essentially order the abstracts by their perceived relevance in a weak ordering. And in the second set of judgments, order the pages related to these abstracts again in a weak ordering. So if we wanted to interpret these judgments as absolute feedback, we have to do something about, we have to worry about biases, right? So for example, are we biasing the user to click on link number 1 just because it's link number 1? Or are users actually making a kind of objective decision that only depends on the abstract that was presented and doesn't account for the position at all? So we know from the previous study that roughly link 1 and link 2 receive equal amounts of attention. So what's the reason why they click more often on link number 1? Is it actually more relevant, or because they trust Google and think that Google gives them a good link as number 1? So here's the results for the normal condition. Here's the results for the swap condition, where the top 2 links were swapped. What the columns say is they didn't. So this column means they didn't click on either of the 2 links, link 1, number 2. Here they clicked only on 1, but not number 2. Not number 1, only link number 2, clicked on both. So if you compare how often they clicked only on 1 or only on 2 in the swapped and in the normal condition, it's rather similar. So what you would expect if people actually only evaluated relevance based on the abstract is that in the swap condition, you wouldn't have 33 versus 4, but you would have 4 versus 33. And that's clearly not the case. Since we have relevance judgments, we can actually look at, well, what did the judges think about the relevance of a link? So this row shows the cases where link number 1 was more relevant than link number 2 as judged by the judge.
On abstract or
this was judged on abstracts. And it's 19 to 1. So if the more relevant link is ranked number 1, people pretty much always click on it, or the more relevant looking abstract. Here, this is the same row. And what we would expect to see if people, again, judge only based on the abstract, if we would want to see something like 1 to 19, which is not the case, clearly. So what we can conclude from this is that position at which the result was presented has a huge influence on whether people click or not. And so that there is this bias that the order of presentation clearly influences not only where people look, but also where they click. So there is this kind of trust bias or presentation bias. So I think we can reject this hypothesis. Second thing that's problematic is, do people really just evaluate the abstract by itself, or does the kind of the relevance of the surrounding links or the surrounding abstracts also influence their decision? So what we've done here is we've we've got from the relevance judges a ranking of the abstracts by relevance, so from 1 to 10. And then here, this is the average rank in this ranking of the clicked links in the normal and swapped condition and in the reversed condition. So presumably, Google does a fair job of ranking. So what they saw here in the reverse condition is kind of less relevant links or less relevant abstracts. So it turns out so what this means here is, so if the users always click on the most relevant looking abstract, this would be 1. So the higher, the less relevant are the links that they clicked on. So again, there's just a significant difference between the two. And essentially, if you embed a mediocre link within bad links, people are going to click on it. If you embed a mediocre link within good links, people are not going to click on it, right? So the fact that user clicks does not only depend on the relevance of the link itself, but it also depends on the relevance of the links around, right?
When you reverse condition, you would reverse one by each Google result page. So it went from 10 to 1.
Yes, right. So again, we have a bias here. So clicks cannot be interpreted as judgments of just this link, but have to be taken into account. It has to be taken into account what was presented around the link. Right? They're given the list in randomized order. Is there a bias in?
Do I think that the top one's more relevant?
The judges did not know what was presented top. So they were given the list of Google results.
But my job is to say whether or not it's relevant. And given a list of things, maybe
I don't know. We didn't check for that, actually. We did tell them it's randomized, yes. I'm not sure whether they still... I mean, there's probably an attention kind of decay, right? So we used 5 judges. They were given the same random order, and we had some overlap for inter-judge agreement. So some of the queries were judged by multiple people.
I have sort of a related question. I'm told I don't see quite how it impacts you. That you're talking about absolute relevance, but if I'm scanning a list, marginal relevance is really what I care about, right? So I may not click on the second thing, may be completely relevant, but overlapped by the first one that I already clicked on. So does that? I don't see how that would affect the result. Is that a concern, or is that true relevance is enough of a proxy for what you're getting at?
I don't think
you know what I'm saying. Let's say you have 2 results. You give me a list. The second guy could be perfectly relevant. I already clicked on the first, and I can see from the abstract the second guy is subsumed by the first guy. So the marginal relevance of the second guy, given that I looked at the first, is 0.
Right.
The relevance of your scoring it is 10.
Right. So we did not look at dependencies between clicks, between abstracts, essentially. We treated them as independent. But I think that's a great issue that you want some diversity in your rankings and in your function. Yes. No, we didn't really.
There's a lot of redundancy, right? So the queries are not on videos, and the search engine is doing well. We expect that most of the queries are relevant.
Well, I think they're still, they had specific questions, so it's not really relevance only that we're evaluating. Actually, we asked the judges to evaluate in how far it brings you to the answer to the question. So it's not really relevance that's relevant to the topic, but it actually helps you answer your question. So, yeah. Yeah.
So a 0.6 difference would indicate that they looked at the abstract and found without much significance the right one. So they went down to 8 or 9 to find the most relevant. They were somewhat successful in I don't think 0.6 is a big difference between swaps.
Well, it could also mean that there was much correlation between the relevance and the
Yeah.
Yeah.
Which is contradictory to the previous conclusion that it's the position that's most important and they're drawn by the player. Whereas here they are presented with the abstract and they somewhat have some bad judgment, but it's not that big.
So actually, one thing that happened in the reverse condition, people scan more links. So it actually went up significantly that people look at more abstracts before they commit to a click. So they do seem to go further down. Right, but there are a lot of dependent factors here, and I'm not sure we've actually figured out all the dependencies. Yeah. Okay, but I think what these two types of bias tell us is that it's really difficult to interpret clicks as absolute feedback. So we would have to account for like how much does the position influence the decision versus how much does the abstract influence the position, which seems to be really hard to estimate or to tease apart. And also we would have to kind of judge how good the links around that link are, and well, that's something we don't really know. So I think this makes the interpretation as absolute feedback somewhat difficult. Now, well, so I think the interpretation that I think we're kind of agreeing here, I think the interpretation is, I think this type of interpretation is getting at what you're saying, and is probably, well, I think it's actually a lot more plausible, and also turns out to be a lot more accurate. What we really want to evaluate is, what we really want to get from the clicks, or what we can only get from the clicks, is kind of relative judgments between the links that the user saw. So you can think about this as a set of options, and that the user is picking the most promising option. So what does it tell us? For example, one reasonable strategy that we've used in the past is this one here. So if the user clicks on link number 3 and has skipped link number 2, well, it's kind of hard to say that link number 3 is 0.75 relevant, but it's probably more plausible to say that it's more relevant than link number 2. Right?
Again, just getting back to what I said before, it doesn't say that. It said that 2 might be more similar to 2, what might be better than 3, but more
Right.
similar to 1.
Right. So there is the dependency issue, which we are completely ignoring.
You still have the contextual dependency.
Yes, you do have a contextual dependency issue, but it's but what we are essentially making here is an independence assumption between the links.
You also look at click duration. In stuff we've done, that turns out to be really important.
We haven't, but I believe, yes. So, and then, I mean, we just came up with a bunch of strategies where we can essentially interpret clicks not as these, just as pairwise preferences. So, for example, here we would generate these pairwise preferences. A skipped link that's ranked higher is probably less relevant than a link that was clicked and is ranked lower. So we'll get a preference in this example for 3 is better than 2, 5 is better than 4, and 2. So that would be this strategy here. Or what we've seen in this table with where people look when they click, what turned out there was that the highest chance that they looked at a different link is the one that's immediately above it. So maybe just this strategy here saying, well, we're pretty sure that the user did evaluate link number 4 when he clicked on link number 5, so let's just make a pairwise preference here. So for this particular query, 5 should have been ranked higher than 4, and 3 should have been ranked higher than 2, but not 5 than 2. Here's another one. Well, presumably people kind of, if they do multiple clicks, once they come back, do the first click, come back, make a second click, maybe that a later click is more relevant than an earlier click. Seems reasonable. Again, we get these pairwise preferences. Oh, sorry. This is the one I've explained before, that we just take the adjacent links. This is the one here where we just look at the last click that the user makes and say everything that's above it and it wasn't clicked on is less relevant. With the assumption that the last click is often, well, where they actually found the information, or more likely that they found the information. They could have given up too. But. And the last one here is doing a preference if the user clicked on link number 5, that they actually have evaluated link number 3 and link number 6 here, and that so 5 should be ranked higher than number 6, which it already is. But. So now we can go through, take our manual relevance judgments and compare how valid are these preferences that are generated. Mm-hmm. Yeah, right. It turns out that this is the only one that's actually not accurate in our setting either. So here are the results. So this is for manual relevance judgments of the abstracts. So we're comparing how people make use of the information that they have and how well this agrees with the manual relevance judges. And if you look at the interjudge agreement of if two judges had a strict preference between 2 pages, the number that we're presenting here is the fraction of times that this preference agrees between the 2 judges. So in roughly 89, 90% of the time, the 2 judges agree if they have a strict preference. Now, we can compare that against the preferences that we generated from the implicit feedback. So for example, whenever we generate a preference according to this strategy here, click better than something that was skipped higher in the ranking, and compare that against the manual relevance judgments, these preferences are roughly 80% correct. So, and all of these strategies are actually significantly better than 50% random that you would expect if there was no information in them. And they're actually surprisingly close to what you could possibly get from explicit feedback that you could ask a user to give you.
What does Google ranking get on this? If Google ranks
I don't remember, but it's very high, just because you have these biases in there. So one thing that you note about all of these strategies, except for the last one, is that they're actually contradicting Google's ranking, right? So they're giving us useful information in the sense that they're telling us something with this ranking is wrong. So in that sense, they're actually not, well, I'm going to get to that later. So, but clearly this one is the weakest one. The click is better than an earlier click is just marginally.
Excuse me if you already said this, but are the judges judging based only on the abstract or based on the entire page?
Here, only on the abstract. And we're going to have another set of judgments that are only on the page, and they didn't see the abstract. Uh-huh. I haven't really looked at the data, like actually trying to analyze particular path. So actually one thing that we're going to see is, so remember these are the relevance judgments based on the abstracts. So when people make a click, so can I come back to that later? Okay. Yeah.
I know when I've used Google Web to find something, I'll find the answer in the abstract and not have to go to the page. So
Right.
is there any accounting for that?
No. And that actually happened in some of the examples. So if it like says Fleming was the discoverer of penicillin, we didn't catch that. Now let's look at how these strategies are affected by these potential biases in the data, right? So this is for the second study where we have these three conditions where we messed with the rankings, right? So we changed the retrieval quality and we changed the order in which the results were presented. And in all conditions, except for the earlier click, even if we messed with the ranking, the results are still significantly different from random. So in all conditions, we do get information. They're actually pretty homogeneous across the three conditions. So we are fairly robust to these biases of where things were presented and what was the context in which it was presented. So the click versus earlier click actually degraded quite a lot in the other conditions. I'm not sure whether this is actually real. There are huge error bars on here. But clearly, this seems to be the weakest strategy and the one that's most affected also by the abstracts. Now, what we are ultimately interested in is what do the clicks tell us about the relevance of the pages, right? So this was all comparing the judgments of the abstracts. So here's again for phase 2, now over all conditions. This is the accuracy based on the judgments of the abstracts. Here's the accuracy compared to the judgments of the actual pages. So first thing that you can see, the interjudge agreement goes up a bit, which seems reasonable because pages contain more information and people are probably better able to judge the relevance. Second thing that you see is that in all, again, removing click was better than earlier click, in all cases, this number is a little bit lower than the other number, but it's only, the difference is fairly small. And again, all of these judgments are better than random.
Your inter-rater agreement 89.5?
This is for the second part of the study, where we actually had so there's some variance just by the fact that it's a different set of people. And it's also that we used a slightly different judging mechanism here. For work that we're doing with Philip, we didn't have the judges sort each batch of 10, but we had them sort across all retrieved results for one question. So there were like these 2.5 or so queries, and so we put all of these in one batch and had judges sort them, which means they had to sort a bigger set, which probably accounts for the fact that the agreement gets a little bit lower. Mm-hmm. This compared to this here? There was one main judge for a particular question, and we just used his judgments. So what we can conclude from this, that these pairwise preferences, despite the fact that the user's judgment was based on the abstract when they made the click, they actually tell us give us quite accurate information about the relevance of the pages. Clearly better than random. So there is definitely some signal in this data. One thing that's kind of interesting, the only one that goes up is the click versus earlier click from abstracts compared to pages. And I'm trying to wrap my head around that. But one explanation could be that there are misleadingly good-looking abstracts, and people look on the best-looking abstract first, go to the page, oh, that wasn't it. Then actually click on a less promising-looking abstract next. But when they find the page and look at the page, oh, that actually contains the information, right? So that actually could account for this. But again, the error bars are pretty big. I'm not sure whether we're actually seeing something real here.
The presumption that effective click is necessarily because better than the first click. I mean, if a person clicked on 3 links, then you might conclude that the second one was better than the first. But often the last link is the worst because that's when you stop looking.
Yeah,
Okay, think about
they got they get so desperate. Yeah.
And so if the second link is used with the last link, then it's quite often likely to be worse than the first link.
Yeah, that's a good point. And I think if you wanted to get any useful information out of this strategy, yes, I think that would be a great way of modifying it.
That the fact that it went from horrible at 46 to slightly less horrible at 64 may not really be.
And maybe we actually really want to just look at the subset of preferences that you mentioned, and those might actually be much more accurate than the global set.
I haven't got the number in mind, so I think it's 243 total queries. Divided by, yeah, it's in the ballpark. Queries per question. You have to explain you have a query, you put a query, it's doing a query. Then when you start questioning it, it works more slow. And going on the last query, that's the last question.
Yes, and that is actually what Philip looked at in much more detail than here.
So these numbers are based on the entire study as opposed to just the success. In other words, that led them to success.
Yes, we did not just focus on so we did assess also whether they actually found the information, but this is over everything. No, and I think only very, very few people did actually go to the second page. Oh, that's what you mean by requery.
No, I'm trying to differentiate. So to make it the second page, then it's not called requery. Only you write the requery
Right.
and get the second page.
Right. So one thing that's maybe an interesting number, if I remember it correctly, in roughly 50% of the cases, I think, they didn't click on anything but just reformulated. So there were a whole bunch of queries where they didn't bother to click on anything.
Okay, so some might requery like 2.2 times or whatever. How did people's first time queries differentiate? One might put an explicit question, some person might use a keyword approach. How did that differ? Did that affect any people's?
We didn't really look at the types of questions that people asked. So one thing that Philip did look at is, now for the second set of questions, we had judgments across the whole, over all questions, all queries that were asked for one question. So we can kind of look at were the results retrieved for the first query less relevant than the results for the second query and for the third query. And that seemed to be the case. So people managed to write better queries. Their queries actually improve, and they retrieve more relevant results. Again, Philip can talk more about that. OK, so I think I want to stop here. It's great that I got so many questions. What I'm not going to talk about, what I let Philip talk about, is what are the learning algorithms that you can actually use to learn from these pairwise preferences.
One slide on that, or at least point people to the paper.
Well, I can do one slide. Oh, OK. OK, so well, then the question is, how do we learn from these pairwise preferences? So typically in machine learning, we have these like classification kind of data, right? This is relevant, this is not relevant. But we typically don't have this data, this is more relevant than this, right? We need to learn an ordering function from these pairwise preferences. And so what we came up with is a support vector machine learning algorithm. And the basic idea is that we want to learn a ranking function that fulfills as many of these pairwise preferences as possible. And for mathematical convenience, the kind of ranking function that we're using is a linear function. So we have a function which we call the retrieval status value. And this is just one value that assigns a particular number to a query in a document, and then you rank the results by this number. And the way this number is computed is a linear function, and you would, for example, have a feature, how many query words occur in the title of the document, or how many query words occur in anchors pointing to that document, or what's the page rank of that document. And each of these features here is multiplied by a weight. And what the learning algorithm learns is the weights. Right? So in a more compact representation, we have a linear function with a weight vector here and a feature vector that describes the match between the query and the document. So what we have from our pairwise preference data from the click-through is that we get these preferences saying the user prefers document I over document J for a particular query. And we can just turn that into a linear constraint, right? So the user says this should be ranked higher than that one. Well, that means the retrieval status value for this document, so this linear function, has to be larger for this document than for that document. So we can think about this as just writing a big set of constraints, one for each pairwise preference that we get from the click-through data, and then find the W that fulfills most of the constraints. We probably can't fulfill all of them. So I can write that as a big optimization problem. So this is the set of linear constraints, one for each preference. And if you want to turn that into an SVM, you put a regularizer, so you want to minimize the norm. And you use these slack variables to kind of get an upper bound on the number of constraints that are violated. So this turns out to be a nice optimization problem. It's convex, quadratic, and you can use almost the same methods as we use for classification to solve these optimization problems. So SVM Lite does it. The basic idea is the same, that you have these pairwise constraints. In the ordinal regression case, you have a different distribution that you're sampling over, right? You have just one distribution. Essentially, you have a distribution that says item and rank. Here you have a distribution of query and ranking, right? So the data generating distribution is the same, but the underlying machinery is very similar. Yeah, they translate this problem into a pairwise problem, yes. So essentially the optimization problem that you get is pretty much the same.
It looks to me like, if I subtract, the P or whatever, subtract the right side from the left side, you end up with this exact same equation. I just did it.
Yes, you do. That's
so as from like a purely practical standpoint, it looks to me like I could take, I guess kernels might screw this up.
No, we can do kernels too.
Okay.
It just becomes really slow.
I want to do it, for any linear algorithm, I want to logistic regression for example.
Yeah, you can do that.
You just throw in the pair differences.
Yeah.
And now I can use any standard toolkit just by changing the input to the learner without having to even write it in the postscript.
Yes.
So just product, that's
No,
fantastic.
that's great. Saved me a lot of time. Uh-huh. Okay. So I guess I have to go through all the slides anyway. So we ran an experiment where we wanted to see if we could adapt the ranking function to a particular group of users. So for example, what I've done here was create a meta search engine that just grabs the top 100 results from 5 search engines and then re-ranks them according to the learned retrieval function that just uses the preferences click better than skip above. And then I gave the search engine to a group of 20 of my friends, which were all German machine learning researchers, so a pretty homogeneous group. And just asked them to use the system just like any other search engine. Collect the training data and test it later. Okay, I'm going to skip the test methodology. So yeah, what you get is, yes, it does improve. Trust me. And here are the features that it actually learned. So these were the features that I put in, and I just kind of brainstormed what kind of features I could put in that would be helpful differentiating between different users. So what I put in was, for example, like what was the rank in all the base search engines, right? Or was it top 1 by Google? Was it top 1 by MSN Search? Was it in the top 10? Or a whole bunch of features like that. Then I put in all the domain names that the results were coming from, assuming that, well, they might have preference for particular domains, and so on. So I like the lengths of URL and characters, stuff like that. So what you see here is the weights that it learned. So high weight, high positive weight means a document, a query document pair that fulfills this feature is going to get ranked higher. And a large negative weight means that it gets pushed down compared to like an average. So what you can see here is like this one. It's probably affected some by presentation bias. So what's the cosine between the query and the abstract seems to be important. Then is it in the top 10 from Google seems to be the second most important link, second most important feature. And so on. What's interesting about this particular group of users is, so a pretty high weight. So when they were looking for machine learning articles, they found it in sites here. So they preferred links that come from sites here to links that from somewhere else.
There's a parameterized feature that you learn post has the name X, or you actually specified sites here?
No, I have one feature for every domain on the internet.
Oh, okay.
So overall, this is like, I don't know, a couple of 100,000 features. So then, essentially, I took all. I think I just split the web address, the name, into chunks. So what it also learned was that they preferred links from .de, so they were German. They were using that to do all kinds of things, like find out about movies and stuff. And they didn't like, for example, links from Finland, right? So I think it does reflect the preferences of this particular group of users. And so in our evaluation, it actually did turn out that in kind of a blind test, they did prefer the rankings that were generated by this ranking function over rankings that were generated from Google, and also rankings, unfortunately, by MSN Search. Yeah. So that it's not ranked top 1 by any of the 5 search engines. So one problem with doing this linear analysis is that all the features are dependent, right? So
the fact that it's not ranked in top 10 implies that they're not ranked top 1.
Well, again, they are one subsumes the other. So really, what this means. I don't really know.
If it's not in the top 10, it's also not in top 1.
Yeah. Yeah. So. Okay, so let me wrap up. Oh, so one thing that I want to also say, we've also started looking at generating these preferences across queries. So for example, for my SVM example in MSN Search, you'd see I don't click on anything here, but I reformulate the query to support vector machine, get reasonable results, maybe click on this one here, and then also generate preferences that tell me, well, for this query, the next time, and for that user or for that user group, really you want to do something and maybe include results from here or also over here. Right? So we learn kind of dependencies between queries in these query chains. But again, Philip can tell you more. So, okay, conclusions. So I hope I've convinced you that you can get somewhat accurate feedback from click-through data, but that it's probably going to be a lot more accurate and easy to handle if you think about it in terms of relative preferences, kind of relative choice among the options that the user saw, than trying to interpret it as absolute feedback. The second thing is that you can use machine learning methods to learn from these pairwise preferences, and that they're actually quite easy to handle. And so here's a list of current and future things that we're doing. So as I said, we're exploiting these query chains and people reformulating queries. We have 2 test beds, one for the Cornell Library web search and one for the physics ePrint archive that we're using to gather data and to evaluate our methods. Philip's currently finishing up an implementation of all of this, which he calls the Osmond search engine, which is going to be on the web soon. Also, Philip's done a study on how robust is this setup of generating preferences to noise, changes in user behavior, and we're planning on looking at click spam as well. And at least for these 2 here, we've done simulations with a simulated user model. They seem to be fairly robust. I think on a broader scale, I think it's an interesting machine learning problem to come up with a learning theory of this learning from preferences and this interaction of what you present is what you're going to get feedback on, right? So there's the trade-off between exploration and exploitation that plays in there. So you have a kind of more of a kind of a process model of learning, really. And we also want to continue looking more at studies of users, because I think really if you want to make justified use of behavioral data, you have to learn a lot about what your users do and how they behave. Okay, so thank you very much.
Thorsten, thanks for a great talk. You got lots of questions.